Welcome back, Design Junkies, to Mechanical Engineering Made Simple. We are uh, ripping the cover off the foundational knowledge that bridges the mechanical, electrical, and electronic worlds. We're
Yeah.
talking about the core data that, the modern electromechanical design engineer relies on every single day. Our mission today is to cut through the noise, explore the essential shifts in the toolkit, the absolutely crucial industry standards that prevent catastrophic failure, and the complex hidden calculations lurking inside what seem like simple machine elements, things like clutches, springs, and fasteners.
And that toolkit shift is, I think, the perfect place to start. What's truly fascinating is just the evolution of computational power. I mean, not that long ago, if you were calculating a complex gear train or a dynamic stress analysis, you were relying on things like, say, the Texas Instruments 85 or the Hewlett-Packard 48G.
Those were revolutionary at the time.
They were, but you still had to manually manage steps that are just completely automated now. Today, powerful software like Mathematica or MathCAD, they automatically handle these complex processes.
Like what specifically?
Well, logarithms, trigonometric functions, even finite element analysis pre-processing. Things that once required you to go look up manual tables and do these, laborious steps by hand. The result is a design process that is quicker, it's profoundly easier, and it is drastically more accurate.
That speed and accuracy are non-negotiable in modern design. But here's the thing. Despite all the gigabytes of processing power we throw at a design, the foundation is still, well, millennia-old geometry. Let's start there. For you, the core rules of plane geometry aren't just academic concepts, right? They're the blueprint for drafting and mechanism design.
Absolutely.
It's almost too easy, I think, with complex CAD software to forget the simple geometric constraints that define manufacturing success.
It's the difference between just drawing a line and defining a relationship. Take the simple circle. It defines nearly every rotating or oscillating component we design.
Gears, cams, linkages.
Everything. Now, we assume you know that a line tangent to a circle touches at a single point, but the critical takeaway for drafting is that the line connecting the center to that tangent point is always perpendicular to the tangent line itself.
Okay, and why is that specific perpendicular relationship, that 90-degree rule, so critical for a design junkie?
Because that 90-degree rule is what defines the entire basis for, say, tool path definition in CNC machining, or for determining pressure angles on critical components like gear teeth or cam followers.
I see.
If your CAD model doesn't strictly adhere to that geometric axiom, the part won't function. Or it will fail, and fail rapidly. It's the pure truth that ensures accuracy in manufacturing.
Pure truth.
Yeah.
That leads us directly into the analysis of dynamic change, which means, well, we have to talk about calculus. Now, we aren't going to turn this into a math lecture, but we do need to discuss why advanced math is so indispensable for analyzing systems that are constantly in flux.
Absolutely. And look, we often need an initial rapid estimate, a quick check on the back of a napkin before we fire up the full simulation software. This is where differentials shine. A quick way to find the approximate change in a function, let's call it d, is using the differential equation. D is equals f prime of x dx.
And that approximation is often a huge time saver compared to calculating the exact change between 2 points, especially if the change is really, really small. So for example, if you have a nonlinear function like, say, y equals 2 times x to the power 3 halves, and you just want to know the approximate change in y when x moves from 9 to 9.02, that differential calculation is nearly instant, and it's extremely close to the exact answer.
Precisely. It gives you immediate feedback during that initial conceptual phase when speed is, frankly, more important than the last decimal point of precision. If the approximation tells you the change is too large or too small, you scrap the idea before you waste hours on a detailed model.
But hold on. If I'm relying on that differential approximation, how big is the risk of error? Is that only safe for a rough estimate, or can I rely on it for critical sizing?
That is an excellent point about professional judgment. For safety-critical components or for final sizing, you always use the exact calculation or the simulation. Always. The differential is a tool for rapid iteration, for checking basic feasibility and vetting boundary conditions early on. You use it to make sure you're pointed in the right direction, not to sign off on the final design.
Smart. Okay, so we've covered rapid checks, but what about when the system you're designing involves, complexity, multiple variables changing at the same time? A standard derivative won't cut it then.
No, it won't, because engineering is rarely that simple. It almost never involves just one changing dimension. When a system involves multiple changing dimensions, partial derivatives become absolutely necessary to analyze the rate of change. Think about something like a rectangular container filling with fluid. Its volume, V, is a function of its depth, x, width, w, and length, L. If all those dimensions are changing at the same time, maybe due to thermal expansion or a dynamic structural deflection, you need to find the rate of volume increase by partially differentiating the volume expression, V equals x times w times L.
So if I have a scenario where that container's depth, width, and length are all increasing at, let's say, 3 inches per minute, you have to use partial derivatives to understand the instantaneous rate of volume change.
It's the only way to accurately model that complex interdependent behavior. It moves you from simple linear modeling to the reality of multivariate physical systems.
Okay, we've established the language of forces and changes. Now let's talk about the physical components that contain and manage those forces. And that brings us to the most overlooked and sometimes the most dangerous part of a design: fasteners.
Fasteners are critical infrastructure. I mean, they're meant to be predictable, reliable, and strong. Yet, we face a serious global crisis. Counterfeit bolts. The sources show this is a major real-world concern.
The importation of them.
Yes, counterfeit bolts marked with false head markings. They look right, but they are made from inferior steels, often without any of the necessary heat treatment.
And the consequence isn't just slow degradation. The failure often happens right during installation, which can be disastrous. We're talking severe injury, property damage, or immediate structural collapse. So how does an engineer, looking at a huge bin of bolts, distinguish a legitimate life-saving component from a deadly fake?
That's why standards are our shield. The industry combats this risk by rigidly defining strength and composition through standards like SAE, the Society of Automotive Engineers, and ASTM, the American Society for Testing and Materials. A counterfeiter can fake the head marking, but they can't fake the underlying metallurgy.
Can you give us a concrete example of that standard?
Sure, take the SAE Grade 8 fastener. You see it all the time in heavy machinery. It must be made from medium carbon alloy steel that has been quenched and tempered, Q&T. That specific processing results in a guaranteed high-proof load of 120,000 pounds per square inch and a minimum tensile strength of 150,000 psi.
Wow.
And that standard holds true across a wide range of common diameters, from a 1/4 inch all the way up to 1.5 inches.
So the Q&T process, quenching and tempering, it isn't just a material choice, it's a structural necessity that determines how the fastener fails.
It is. A proper grade 8 bolt will typically fail in a ductile manner, meaning it will stretch and deform before it ruptures, which gives you a warning sign. An inferior or counterfeit bolt lacking that tempering might fail brittly. It just snaps without warning, which is catastrophic.
And for those of us using metric components?
Same principles apply. You use the numerical markings on metric hex cap screws like 4.6, 8.8, 10.9, and 12.9. Those numbers denote the strength classification and material grade. For structural integrity, adherence to these standards it's absolutely non-negotiable.
Moving beyond mechanical fasteners, welding is another critical joining method that requires absolute standardization. It's a fusion process, right? So if it's performed correctly and the preparation is right, the resulting joint can theoretically be as strong as the original parent metal.
And that, if performed correctly, part depends entirely on organizations like the American Welding Society, or AWS. They provide the specific designations for all the various processes. For example, knowing the difference between GMAW, that's gas metal arc welding, and TIG welding, or even the various metal cutting processes like plasma oxygen cutting, POC, or oxy-fuel gas cutting, OFCA.
And that quantification of strength is key for the designer. If I specify a weld, I need to know the force it can actually bear.
Exactly. We can turn a physical joint into calculable forces. If you're designing a structural frame and you specify a fillet weld with a 0.25-inch leg and you use a high-strength 80,000 psi weld rod, you can quantify that. It provides an allowable unit force of 4,125 pounds per linear inch.
So you just do the math.
You do the math. You calculate the force the frame needs to bear divided by that unit force, and you know exactly how long your weld bead needs to be.
Calculations are one thing, but, shop practice is another. When we talk about welding massive sections of steel, what are the shop floor practices that prevent a design failure?
Temperature control is everything. Large sections of thick metal, they require preheating, sometimes up to several hundred degrees.
And why is that?
To prevent thermal shock and minimize distortion or cracking as that molten pool cools, the preheating minimizes the temperature gradient across the material.
That makes sense for thick material, but what if the material is really thin, say less than 1/10 of an inch?
For thin materials, you do the opposite. You use heat sinks, and these can be as simple as, say, wet burlap bags placed right next to the weld zone, or specialized copper blocks.
To draw the heat away.
Exactly. They draw heat away quickly to prevent localized buckling or warp. And here is a crucial rule that gets violated all the time in rush production. Welded parts should never be water quenched immediately after welding.
Why not?
Rapid cooling causes distortion and, even worse, harmful changes in the internal grain structure. It compromises the integrity of the weld. You have to let them air cool naturally to ambient temperature.
That attention to thermal details brings us neatly to the electromechanical interface, starting with the unassuming spring, a component that harbors a critical, hidden chemical danger. Springs often need environmental protection, usually by electroplating with metals like bright zinc or cadmium.
And that plating process, while it provides corrosion resistance, is a chemical ticking time bomb. The process, electroplating, it unfortunately introduces atomic hydrogen into the material structure of the spring steel. This causes what we call hydrogen embrittlement.
Hydrogen embrittlement, that sounds terrible. What happens if you skip the preventative step?
If you skip prevention, failure is not a possibility, it's an inevitability. The hydrogen atoms, they migrate to points of high stress like sharp corners or grain boundaries, and they coalesce into molecular hydrogen. This creates immense internal pressure that reduces the steel's ductility. The spring will operate just fine for a while, maybe hours or days, and then suddenly fracture catastrophically under its normal working load.
Wow! So skipping a single process step creates a time-delayed, brittle failure. What's the fix for this dangerous chemistry?
The fix is very specialized. Plated springs must be post-baked immediately after plating. This is a dedicated operation, typically involves oven heating the springs at 500 degrees Fahrenheit for a minimum of 3 hours.
And that gets the hydrogen out.
It bakes out the introduced hydrogen before it can cause damage. If this post-bake is not performed, hydrogen embrittlement will invariably occur, leading to failure. It's specialized knowledge you simply cannot overlook in electromechanical design.
Post-baking saves the day. Okay, now let's move to dynamic power transmission. Specifically, electromagnetic clutches. Their torque rating is vital, and their placement in the drivetrain completely dictates the capacity you need.
That placement is absolutely everything because of torque multiplication. See, clutches are rated for the torque they can transmit at their operating speed. If you have an electromagnetic clutch rated for, say, 280 pound-inches of torque at 90 volts DC, and you install it before a gearbox that has an 8-to-1 reduction ratio,
Then the output of that gearbox is dramatically leveraged.
exactly. The clutch can now drive a load with a multiplied torque value of 8 times 280, or 2,240 pound-inches. Placing the clutch on the high-speed side of the gearbox means you can use a much smaller and cheaper component.
That's a huge mechanical advantage. But when you're sizing that clutch or an equivalent brake, you have to account for the kinetic energy of the entire system, not just the torque rating of the final load.
Right. This is where we return to advanced calculation and the concept of reflected inertia. Inertia is resistance to change in motion. When sizing a clutch or a brake, all the rotating parts, gears, pulleys, shafts, and all the linear moving parts, like a long, heavy conveyor belt, they must have their inertia, which we often represent as WR squared, calculated or reflected to the speed of the clutch or brake shaft.
Okay, let's simplify that for the designer listening. Why reflect the inertia?
Imagine you're trying to stop a train with a small handbrake. The brake doesn't feel the train's linear weight. It feels the rotational inertia of the wheel axle it's clamped to. But that axle is moving much slower than the motor shaft. You have to convert all the kinetic energy of all the moving components, the train, the gears, the motor itself, into a single equivalent inertia value at the speed of the clutch shaft. If you fail to calculate that reflected inertia, the clutch will be undersized, it'll burn out prematurely, or the brake just won't stop the system fast enough. It ensures the component can handle the total kinetic energy of the entire system it is responsible for starting or stopping.
And tying the whole electromechanical system together is, of course, the motor itself. Motor nameplates give us crucial data, but there's a key distinction about speed that we really must address.
Yes. For induction motors, you have to know that the motor's nominal full load speed is always less than its theoretical synchronous speed. This is fundamental to how AC induction motors operate. They need what's called slip to generate torque.
So if I'm doing speed calculations for a conveyor belt system, I can't just use the theoretical number based on the poles and the frequency.
Precisely. If you have a standard 4-pole, 60 hertz fractional horsepower motor, its synchronous speed is 1,900 RPM. But the speed you need to use for accurate pulley or gear sizing, the nominal full load speed, is typically 1725 RPM.
That's a big difference.
It is. If you use 1800 RPM, your entire system will run slower than you calculated, and that could potentially cause a production bottleneck. We have journeyed today from, pure geometric axioms all the way to the dangers lurking inside material chemistry. We've synthesized that fluency in advanced mathematics is vital for quick checks and for multivariable dynamic analysis. We've seen that structural standards for components like bolts and welds must be strictly adhered to. They are the designer's primary shield against unexpected failure. And we've highlighted that specialized knowledge, things like understanding hydrogen embrittlement in springs and accurately calculating reflected inertia for clutches, is what determines the ultimate success and reliability of an integrated electromechanical design.
It's a massive landscape, connecting the theoretical to the physical in every single aspect. And let me leave you with a final provocative thought that ties back to our very first discussion about math versus reality. The source material states clearly that even the most rigorous mathematical solutions to complex industrial design engineering problems are, in many cases, approximations at best. So what does this all mean for you, the designer, when the math itself is inherently imperfect? The greatest and most definitive proof of a design's adequacy is always the prototype and subsequent definitive testing. However, there are monumental products and engineering projects, think massive infrastructure or single-build space systems, where producing a full-scale prototype is functionally impossible or just prohibitively expensive. In those critical scenarios where testing is not an option, you must rely entirely on accepted industry standards, the most rigorous calculations possible, and professional historical experience alone. This highlights why mastering every single fundamental rule in your design handbook is not optional. It is the only guarantee you have when the prototype is beyond reach.